Hi, welcome back. So in this video, we're going to talk about how we graph the tangent function. So this process is going to be similar to how we graphed sine and cosine, except you might be a little surprised about what the tangent function ends up looking like. So to do this, we're going to use the fact that tangent of theta is equal to y over x, or opposite over adjacent. So we're going to do a table with some input and output values. So let's start in quadrant 1. For my inputs, I'm going to do 0, pi over 6, pi over 4, pi over 3, and pi over 2. So I'm going to use a mix of looking at the unit circle and looking at reference triangles. I'm going to use the ones with a radius of 2, so I've just taken the radius of 1 or the hypotenuse of 1 and I've multiplied everything by 2 to get these. You can only look at the unit circle if you'd like. It just involves a lot of fractions, and so sometimes I think it's easier to just look at the reference triangles. Also, if you need a review on how those reference triangles work, this is a good time to get it. Then, using the unit circle, I can remember that cosine is x and sine is y, and so I'm looking at y over x, or sine over cosine. So for 0, for example, we would do sine over cosine y over x, which is 0 over 1, and that's just 0. So tangent at 0 is 0. Then for pi over 2, I'm going to look at my unit circle. So y is 1 and x is 0. I have 1 over 0, but 1 over 0 is undefined. So tangent is undefined at this point, pi over 2. Then for pi over 6, let's look at the triangle. So I'm looking at opposite over adjacent. Opposite is 1, adjacent is square root of 3, and so my tangent value is 1 over square root of 3. As I mentioned, you could do this with the unit circle. You would do 1/2 divided by square root of 3 over 2. That's just a big fraction, and you can do it. You can multiply by the reciprocal and cancel the 2's, and you'll end up with 1 over square root of 3 as well. Then for pi over 4, we're going to do the opposite over the adjacent, so square root of 2 over square root of 2, which is just 1. You can see this too on the unit circle. Both the x and the y points are the same. They're both square root of 2 over 2. So when we divide something by itself, we just get 1. So the tangent is 1 for pi over 4. Then for pi over 3, we're going to use our second reference triangle. So we do opposite, square root of 3, over adjacent, which is 1. So we get square root of 3 as our tangent value. You could use the unit circle if you want, do y over x, and you should get the same thing. Just looking ahead a little bit, you can see too, if we go to 3 pi over 2, so the point directly below pi over 2, that one also has a cosine of 0, so that point is also going to be undefined for tangent. So we'll see that come up once we start to graph more of the function. Okay, so we have our input and output values for the first quadrant, and so I'm going to simplify them here, and I'll also give us the decimal values. So 1 over square root of 3 is about 0.58, and square root of 3 is 1.73. At least approximately. And let's graph these points. So I have 0, 0, I have pi over 4 and 1, then I have pi over 6 and 0.58, and then I have pi over 3 and 1.73. I'm just reusing the same axes for the sine and cosine graphs, so it's just a little small here, but it does the job. Then at pi over 2, I'm undefined. And so this might just be like a hole in the graph, but since I know what's going on here, I know that it's a vertical asymptote. So there's actually a vertical asymptote at pi over 2. Let's talk through why this is the case. So if you imagine our angles as they get closer and closer to pi over 2, on the circle, you can imagine the angle is very, very vertical here. So we're getting that angle closer to pi over 2. So our triangle looks something like this. And this means that the opposite side is very large, it's very tall, and then the adjacent side is really small, it's like really short. So when we do tangent, we would do the opposite over the adjacent. So we'd be taking a really big side length and dividing it by a really small side length. So we have a big number divided by a super small number. So when we take something really, really big and we divide it by something very small, we get something even bigger. So a very big number, let's think about dollars. Let's say you have $1 million. Then you're dividing it into something small. You're dividing it into pennies. So how many pennies do you have left over when you take $1 million and divide it into pennies? Well, you have a ton of pennies. You have even more pennies than the dollars you started with. Anyway, just a little bit of understanding this, but the idea is as our angles get closer to pi over 2, the tangent values get really, really large. So as our input approaches pi over 2, the output gets very big. And so we're getting this behavior of the vertical asymptote, where the function is getting larger and larger as it approaches pi over 2 from the left. Okay, so we're going to just go through now how we repeat the same process for the other quadrants. I don't really think this is that interesting, but I want you to kind of get a sense for what's going on. So if we go back to our unit circle, I just want to point out what's happening with the sign of tangent here, like whether it's positive or negative. So in quadrant 1, we had a positive tangent, but in quadrant 2, we're going to have negative tangent because the x values are negative. So we'll do a positive divided by a negative, which is negative. Then in quadrant 4, we will also have negative tangent because we have a negative y this time. So negative divided by positive is negative. But then in quadrant 3, we actually have a positive tangent again because we have a negative divided by a negative, which gives us a positive. So if we translate this to our graph where we have theta as the input and tangent as the output, we can see that in quadrants 2 and 4, we have negative output values, negative tangent values. But in quadrant 3, so that's between pi and 3 pi over 2, we actually have a positive output, a positive tangent. And we can repeat this process for the negative angle values. And the vertical asymptotes are going to repeat themselves as well. So doing this, we can assume that the graph maintains the same shape, but just below the axis. You can look at the unit circle and see just the way that the cosine and sine values repeat themselves, this is going to happen. And so our tangent function is going to look something like this. I know this isn't like super rigorous, but I just want to give you a sense for how it works, and you could go through all of the quadrants and plot all the points if you wanted to, but I'm just not sure that's necessary for me to do in the video. Okay, so really briefly as we finish, I just want to pull up a graph of tangent here from Desmos, and let's talk about what's happening. So on our graph we have theta as the input and f of theta, which is tangent, as the output. So I wouldn't really say this graph has a midline or an amplitude. We wouldn't really use those words here. But what's really important is that we talk about the period. So the period is the distance of the inputs, so like the amount of inputs that it takes for the function to start repeating itself. So if we look between negative pi over 2 and pi over 2, I'm seeing this as like one section of the graph. So this part of the graph repeats itself over and over, and I see that this distance is pi. So from negative pi over 2 to pi over 2, our distance is pi, and so this is our period. This is how long it takes for the function to begin repeating itself. I just want to point this out because this is different from sine and cosine. Sine and cosine have a period of 2 pi, that's how often they repeat themselves, but tangent has a period of pi instead. Alright, that's it for this video. Thanks so much for watching, and I will talk to you in the next one.